Okay, so if you're a developer, you know this feeling, right? You've done it a zillion times. You write some beautiful, elegant code, you hit that compile button, and boom, magic. An executable file just appears out of nowhere. But what is that magic? Seriously, what is actually going on inside that black box between your code and the machine?
And look, this isn't just some, academic question for a trivia night. The answer to this is the key to unlocking some serious performance from your hardware. It's what separates someone who just writes code from someone who can truly engineer it.
So let's get into it. If you want to write seriously fast code, you've got to know what's happening underneath all those high-level languages we use every day. It's time to pull back the curtain and see what's really going on. Most modern programming languages, they do an amazing job of insulating us from the raw hardware. They make our lives so much easier, but that comfort comes at a price. It kind of hides what's really happening with performance. Well, today, we're going to break through that insulation. And the bridge, the thing that connects our code to the machine, is a language most developers almost never see: assembly. Okay, so when you hit compile, it feels like one single thing happens, right? But it's not. It's actually a whole 4-stage journey that your code goes on, step by step, to become something the machine can run. First up, you have the preprocessor. Honestly, you can just think of this as a fancy find and replace for things like macros and include files. Pretty straightforward. Then comes the star of our show, the compiler. And this is the really important step for us today, because this is what translates your high-level code into assembly language. After that, the assembler takes that human-readable assembly and turns it into pure binary machine code. And finally, the linker comes along and stitches all those different pieces together into the single final executable file that you can actually run.
And that brings us right here to the main event. We've arrived at the destination of that compiling stage, the most direct way a human can talk to a processor. Let's meet assembly language.
Okay, just look at this. It's pretty wild, right? That one single, simple line of C code on the left, it explodes into 3 separate assembly instructions on the right. And here's why. The CPU can't just add 2 numbers that are sitting in memory. It doesn't work that way. First, it has to use an instruction like movel, that stands for move long, to copy the first value A into a super fast little storage spot right on the processor itself called a register. Then, it uses addl to add the second value B to that register. And finally, it has to use another movel instruction to copy the result back out of the register and into memory where C is stored. One simple idea, 3 distinct steps for the machine.
So what exactly is assembly then? The simplest way to think about it is this. It's the closest a human can get to reading the raw ones and zeros that the processor actually understands. Those little codes like movel and addl, they're called mnemonics, basically memory aids, and they match up one-to-one with an actual operation the chip can perform. This is the literal blueprint of what your program is telling the computer to do. No abstraction, no filter.
Let's get even closer and just dissect one of these instructions. Let's take addl %edi%ecx. The addl part is what we call the op code. That's just the operation we want to perform. In this case, add long. Easy enough. Then you've got %edi, that's our source. And %ecx, well, this is where it gets a little funky. It's both a source and the destination. So what this one line is telling the processor is, hey, take whatever number is in the EDI register, add it to the number that's in the ECX register, and then overwrite ECX with the new result. Now, if you're looking at that and thinking, that seems a little weird, maybe a bit illogical, well, you're not wrong. It's because the x86 instruction set that most of our computers use today wasn't designed cleanly from scratch. It just kind of evolved over decades, with new features getting bolted on top of old ones. There's a great quote from MIT professor Charles Lyserson that just sums it up perfectly. This is history, not design. Okay, so this is all pretty interesting, but I can hear what you might be thinking. Dude, I write in Python or I use JavaScript. Why on earth should I care about this ancient, super low-level stuff? And that's a totally fair question, but it turns out there are some really, really powerful reasons why you should. I mean, think about it. If you can read assembly, you can literally see what your compiler is doing under the hood. You can see the smart optimizations it made, and you can see the ones it missed. You can hunt down the most obscure bugs. And yeah, sometimes the bugs are in the compiler itself. If you need every last drop of performance, you can handwrite special instructions that the compiler just can't generate. And, my favorite, you can reverse engineer software even when you don't have the source code. It is, no joke, like having X-ray vision for software. And this is really where that knowledge turns into a genuine superpower, because understanding assembly connects you directly to the big secret of how modern hardware gets to be so mind-bogglingly fast. It's not just about making one instruction run a little bit quicker. It's about running tons of instructions at the exact same time. Let me show you what I mean. A traditional scalar operation, like the add we saw before, that's like a little single-lane country road, one car, one calculation at a time. But modern CPUs have what are called vector units, and these things are like massive multi-lane superhighways. A single vector instruction can perform the exact same operation, like an addition, on say 8, 16, or even more different numbers all at the exact same time, in parallel. This is where huge performance gains come from, and these are the kinds of powerful instructions you can see and even use yourself when you're down at the assembly level. And if there's one number you take away from all this, let it be this one. Getting a value that's already sitting in a CPU register, that takes like one clock cycle, one tick. But if the CPU has to stall and go all the way out to main memory to grab that data, that can take over 200 cycles. Think about that. That's a gigantic performance hit. So understanding how your code is actually using those precious registers versus going out to memory, which is something you see laid bare in assembly, that is absolutely fundamental to writing fast software. So, at the end of the day, peering into that black box of compilation, it's not just about, satisfying some nerdy curiosity. It's about gaining a whole new level of control, a whole new depth of insight. It really is a superpower for any developer who's serious about their craft. And that quote from Professor Lacerson we saw earlier, it just perfectly captures this whole idea. He says, if you really want to understand something, you need to understand it to the level you're working at, and then one level below that, because that's where true mastery comes from. That deeper context is what lets you solve the really tough problems and get the absolute best results. So that kind of leaves us with one final question to think about. For developers, that one level below is assembly and the hardware. But what about in your world? Whatever it is you do, what's that fundamental layer humming away just beneath the surface? Because finding that and understanding it, that's probably the real key to mastering your craft.